In the modern world of unprecedented international connectivity, synchronizing time is more important than ever. Global systems like transportation, online communication, and digital broadcast require every second to be accounted for. Most modern clocks use a quartz crystal oscillator to keep time. First, the quartz is cut into a shape of a small tuning fork, and because it's a piezoelectric material, when an electric watch sends a current through a quartz crystal, it vibrates at a frequency of 2 to the power of 15, or 32,768 Hz. A series of divisions results in a 1 Hz signal which drives the watch's second hand. Quartz clocks have incredible accuracy, being off by nanoseconds per hour. However, this small error has significant consequences. Take an orbiting satellite that provides your daily weather forecast, for example. After 6 weeks of using an uncalibrated quartz clock, you could have a distance error of 300 kilometers. So how did the atomic clock reduce the error? Let's turn our attention to Bohr's energy level model of the atom, which states that orbiting electrons occupy discrete energy levels. When a high-frequency photon is absorbed by an electron, it will move to a higher orbital. If an energized electron emits a photon of the same frequency, it will return to its original orbit. The atomic theory is an important concept, so pause the video and complete the 4 practice problems. The answers will be revealed at the end of the video. With that background info, we can finally dissect the atomic clock. First, an oven evaporates the cesium-133 source to emit a beam of cesium atoms that travel without collisions. Next, the cesium atoms are bombarded with radio waves of a specific frequency, causing the electrons to absorb the energy and change orbitals. If the frequency is offset, less cesium atoms are energized. The cesium atoms are then filtered through a magnetic field. Those that are energized will be deflected into a detector, while the rest are absorbed by a carbon gutter. Though this is a bit different from the cesium clock's magnets, try out this problem to test your understanding of the magnetic deflection of charged particles. Let's get back to the cesium clock. The final step involves the detector relaying its information to a servo control that adjusts the oscillator. If fewer particles are detected, an electric signal will be sent to increase the frequency of oscillations. But what exactly is the oscillator? Well, it's none other than quartz. Recall that a piezoelectric material can convert electrical signals into mechanical vibrations. It can also work the other way around. The quartz vibrations can be transformed into an electric signal that determines the frequency of the radio wave emitted to the cesium atoms. This negative feedback loop will continuously recalibrate the oscillator, and that's what makes the atomic clock so accurate. As such, in 1967, the second was redefined as the duration of 9,192,631,770 periods of radiation corresponding to the transition between 2 hyperfine levels of the ground state of the cesium-133 atom. The atomic clock sets a standardized time for people all around the globe. However, even though you may not have cesium-133 isotopes in your homes, the data acquired from atomic clocks are uploaded to online databases and broadcasted to your everyday radio-controlled clocks via EMR. So that's the end of my atomic clock video, but before I leave, let's go over the 5 physics questions. Question 1. First, find the electron's change in energy as it transitions from its third orbital to its first. You should get negative 2.11 electron volts. Next, use the Planck-Einstein relation E equals hf to solve for frequency. Question 2. The electron can jump twice from n1 to n2, then n2 to n3, absorbing 2 photons. Or the electron can directly jump from n1 to n3, absorbing 1 photon. In total, 3 different types of photons can be absorbed. Question 3. We start by substituting the universal wave equation into the Planck-Einstein relation. To solve for wavelength, manipulate the equation E equals hc over lambda and substitute in the missing variables. The wavelength should be 299 nanometers, which is slightly under the minimum threshold for visible light. Hence, ultraviolet light is absorbed. Question 4. De Broglie's model describes electrons as standing waves, which oscillates in simple harmonic motion. Question 5a. Using the right-hand rule, you should determine that the magnetic force points upwards. Question 5b. If the particle is in uniform motion, F net must be 0. Hence, the electric force must be equal in magnitude to the magnetic force. Finally, manipulate the formulas Fe equals Eq and Fb equals QVB and substitute in the known variables. Question 5c. The electric force points down because it's opposite in direction to the magnetic force. The electric force experienced by positive charged particles follow the electric field, so the field must point down as well. Therefore, plate 1 is positive and plate 2 is negative. Thank you so much for watching my video. Bye.